This is now the fourth and final presentation on the course Environmental Change, and this one we're going to, rather than looking back to the past, so in the first three we looked in the recent past, the medium past, and even quite far into the past, the geologic past. And today we're going to look at models and predictions for the future, and how are these models made, and how do they project? Climate change models have been made from the Intergovernmental Panel on Climate Change. These are based on several scenarios of emissions over the next 100 years. They use computer models which predict temperature, so temperature of the air, the sea temperature, but also the amount of precipitation and snow coverage. But these are very complicated models because, as you can imagine, it doesn't rain the same everywhere around the world at the same time, and they have to model a lot of areas, a lot of weather stations they get data from. And these are what their projections and their scenarios look like. And here we have emission scenarios, so it's not just, let's say, measurements that they take, but also they do economic models, and they have different scenarios, economic scenarios, and depending on which economy they're expecting in the future. So a very high industrial growth, that's what you see in A1F1, a very high industrial growth which continues up until 2080. And as the economy improves, so does the amount of CO2. So this is a little bit of a base. Other scenarios which are similar, A2 says a more steady growth rather than a large growth. And then other economic scenarios look less good, where actually the industrial part declines. So this is how they build them. So they look at the future concentrations of CO2 and CH4 based on the measurements that we do now. So we have a pre-industrial level of about 200 parts per million of CO2. Yeah, so for every million particles in the air, 280 are CO2. And we see a very large increase. The largest scenario, A1F1, and if you want to know, I'll go back to, if you want to know more, go to this video. It gives you a much more detailed background than I'm giving you now. But the increase is from about 280, about 380 now, up until about 900. So this is a 2.5 increase in CO2, and that means approximately a 2.5 increase in the specific capacity of CO2 in the atmosphere, which is the heat that it holds. And in CH4, it's an increase of around 700 from pre-industrial levels to about 1800 now. And I'm sorry, could somebody close the door? And this is parts per billion. Um, the, the difference between CO2 and CH4 is actually quite big. I mean, between those two themselves. So which do you think absorbs more energy, CO2 or CH4? Danny says CH4. Why? Yeah, you learned it, and that's the right answer. But why? Okay, you're a chemical technologist. So what's the difference between the molecules of CO2 and a molecule of CH4? About the bonds. Well, CO2 is a CO in the middle of two O's. So you have two CO bonds. And CH4 is a C bounded with four hydrogens. There you go. Yes. Hydrogen bonds are one of the strongest bonds chemically, and oxygen bonds are less chemically stable, although they're very stable, don't get me wrong, but hydrogen bonds are even more so. And you have four of them here. and here you only have two. So the molecule is just different. The bonds, there are four bonds which absorb more energy per molecule than CO2. Yeah. So I guess that's a point for Danny for knowing the right answer, or a half point because you didn't know why it was right. So CO concentrations, yeah. Ah. Oh no, I'm just saying that the increase, both of the increases will, so an increase of CO2 will increase the greenhouse effect. Yeah, CH4 has a much more higher warming potential before it breaks down, and that's why CH, on top of my head, I'm not sure how many more times worse it is, or better at absorbing energy for the environment. But yeah, an increase in CH4 is worse than an increase in CO2. Although an increase of CO2 is also bad. Don't get me wrong. Uh, but the sources are different. Yeah. So CH4, the sources are non-industrial really. If they're cows are number one for CH4, but CO2 that comes from cars and that comes from industry. So it's very different levels. This is factories, cars, and this is farming, cows, that kind of stuff, pigs. So here is a forecast of the CO2 concentration levels in the past up to the future, according to different scenarios. Have you guys seen these before in other courses, like climate change? Some people saying yes, some people saying no. I think it's a second year class. So some of you might have seen this before, but the exchange students and the new students haven't seen these before. And in every scenario, it's most important is that some of the scenarios say nothing will change and we'll just continue exponentially, and some of them say we will reach a maximum load. Do you know what kind of curve this is called? It goes like this. It has several names actually. Uh-huh. Hockey stick. Oh, no, because you see this, it's tapering off. But yeah, it's a hockey stick. But yeah. What about like this? It actually has like three or four names, depending on what your background is. Statisticians call it an S curve because it looks like an S. Um, Biologists call this a biological curve because you have rabbits on an island. They will go very very fast, but at a certain time they eat everything up, and there's a maximum what biologists call carrying capacity. So they call it a biological curve, and other people call it a logistics curve. And economists normally call this a logistics curve because at first logistically it goes better. Oh, there you go. Peter got it. I got a point for it. And then at the end, it becomes there's traffic basically. So the first few trucks really increase the efficiency, but the more trucks that come on the road, the less efficient it is, and then you get into traffic jams, and that's why it has a maximum. Yeah, but they have different names. They all mean the same. We can only uh, produce so much, and then we've reached our maximum. So those three: statistical, I mean, sorry, not this way. S curve, uh, logistical curve, and biological curve. I think that made sense. This is a prediction of the surface temperatures. Why would we be interested in surface temperature? Actually, why not? But I've talked about CO2 and CH4, but that's air temperature, and not even the temperature where we are. That's the temperature in the atmosphere, way above us. Why would we be interested in surface temperatures? There are several reasons. Yeah, exactly. Well, it's funny. You guys said at the exact same time. This is where we live. Correct. That's definitely a very important one. Although, if it gets warmer in the Netherlands, I'm not going to cry. The tears will not be flowing if it becomes average temperature a little bit higher. Um, but what is it on the surface that? Yes, yeah, but a lot of it has to do with like water temperatures, also for melting ice and snow. The surface temperatures they affects us a little bit, but worse is the that more water will evaporate, that the El Nino effects will be worse, that the snows will melt faster. So yeah, that's why we see large increases in all of the scenarios, and they're expecting anything from a 1% difference, which is already a lot, to a 5.5%, 5.5 temperature to change. Oh yeah. So this question is, what does A1, A1B, A1T? Those are the different scenarios. So economic scenarios of the world. Like one scenario, they're very complicated, and the one is like everywhere around the world will grow at industrial levels. Others say like Europe won't grow, but Asia will grow. Another one will say Brazil will grow and China will grow and not Europe. So there are so many economic scenarios. And then there are economists who take these scenarios from other economists, and they calculate a lot of data. Yeah, you have different types of economists, and that's how they calculate this out. So as I mentioned, the estimated for the low scenario, which is B1, it's the lowest scenario, the range is about 1.8, and for the high scenario, it's 4 degrees. Yeah, so up to about 6.4. And a lot of they have different types. You have the SRES and TIR, and they both agree. So there are lots of models. I should also say it's not just one model. The data is generated first, and a model is like a formula, and there are different models that use the same data, and that's why you see differences. Yeah, so the one model models our temperature, our climate one way, and another model does it a little bit differently, and that's why there's like an error bar. Um, so near-term projections are insensitive of choice. Yeah, so we we are assuming that even if we were to completely stop all industrial activity, it will still, the short-term impacts are unavoidable, and the longer-term projections also depend on climate model sensitivities. So you see in all three of these scenarios, we have the one that's very dramatic and the one that's less dramatic. The short-term are all quite peaky. Yeah, so it's all about 2 for a lot of all three of these models, while the long-term change for B1 is much lower. And then they make, of course, these maps. So these models, first you saw, I'll go back. This is the temperature for the entire world, and that's something that's quite often reported, that they've measured that the Earth has increased 0.2 Celsius in the last 10 years. But it's also important, I won't say more important, but it's also very important to show the increases in local areas. So here are the three different scenarios. So this was a very light scenario, the increase here. Yeah, so if it's blue, it's increased 0, and if it's purple, it's increased 7.5 degrees. And you see, of course, the impact. Well, you tell me, what do you see the biggest impacts in the scenarios? Yeah, specifically the North Pole. So that means northern Canada, Russia, and others. They agree to a large extent that the North will have the biggest effect. Projections of future changes in the climate. This is one for participation. For precipitation, it's a difficult word. It's slightly different than temperature because it's weather patterns. Predicting weather patterns is just in 2 days is difficult. Imagine trying to predict weather patterns in 100 years. So here we have a change again that's most likely in the high latitudes, and actually a decrease in the subtropical regions. So we expect the wet areas that are already wet to become wetter, and the dry areas to become drier. Yeah, so they expect if it's red, they expect a decrease of 20% rain. This is in I think about 100 years. And in the north, where we are located, they're expecting an increase of 20%. Well, not all of us are there. I think Abel is the smart one. He's in Australia. Of current rainfall. Well, precipitation. So rain and hail and snow, just total precipitation of water coming down from the sky. Well, no, because that's already rain. I mean, if you look at the, I mean, the places where it's red, these are deserts. This is the Sahara. This is the Mojave. These are already very, very dry areas. So the wet's getting wetter and this dry getting drier, and everything is getting hotter, especially in the north. So just living in the Netherlands would be like a warm bath. We'll just walk around. Think of the savings of our heating bills. No, that's not good. That was a joke. Um, so, and in general, there is now a very high confidence. I would say lots of models and all scenarios, even very positive models. There's a confidence in projected patterns of warming, and on the regional scale, it includes changes in the wind patterns, precipitation, and some aspects of extremes and of ice. So remember how the El Nino worked, yeah. So if it's getting warmer in the water, where was that? Yeah, so it's increasing the temperatures in the water. That means that there'll be more water vapor in the air. So monsoons will be worse, El Nino will be worse, tornadoes, we don't know too much about wind, if wind will increase. So some more things uh, in general. Snow cover is projected to contract. And this I got this from a report from 2007, I believe. And I've read articles in the last few years that the snow cover is contracting faster than they even anticipated. I think Iceland is almost completely empty of ice, which is amazing. Greenland, yeah, it's they have an entire empty caverns underneath the ice they didn't know about. So yeah, caverns. So the ice that is like the glacier, the inside of the glacier is now empty. Yeah. So they didn't know that when they made the projections, and now they know that. So it's going faster than we expected. Did I talk about everything? Yeah, yeah, that's a problem because the more the ice melts. So it's two things. First of all, the ice will melt and there'll be more water in the sea, so the ocean levels rise. Secondly, don't forget what's the albedo again? The albedo effect. Exactly. So the ice and the snow reflects the energy back into the sun. Exactly. Thank you, Luke. Also correct. So the ice not only it does it keep a reservoir of water outside the oceans, but it also is there to as like a reflector to stop the ground absorbing the radiation of the sun. So it's not a good thing, no. Sea ice is projected to shrink in the Arctic and Antarctic, and in fact, In the Arctic, it's projected to completely melt. So Arctic late summer ice disappears almost entirely by the latter part of the 21st century. So in about 70 years, there'll be no more ice in the North Pole during the summer. Yeah, yeah. So it's an well, we'll have to lead a good life. I'll have to start living cleanly. Give up some bad habits. So I can make it 90 to see if it happens. But remember, these are people who've been studying this for a very long time. So I have a tendency to listen to experts. It's like you go to your doctor who knows a lot. You listen to him or her. So why don't we listen to the climate scientists? So more climate changes, hot extremes, heat waves, heavy precipitation that will become more frequent. Cyclones and hurricanes will become more intense with wind speeds and heavy precipitation. Well, no, not every year. It just gradually gets worse and worse and worse. But yeah, but like every year we always hear that it was the warmest year in the year ever recorded. It was the warmest, the wettest month every single year. So it may only increase like 2% a year, but in 100 years, that's big. That's a big thing. Um, and it's expected to move poleward, uh, which means in some places more precipitation. Us, really. That's why we're so wet. So right now the weather patterns are spread across from the north to the south, slightly more to the north and the south. So the wettest places on the planet are the north and the very far south, but it'll be even worse. Yeah. So the middle part, it migrates even more to the north and the south. So yeah, so the middle part dries out and the north part melts. A couple of more before we take a break, because it's already about 2 o'clock. Based on current model simulations, it is very likely that the meridional overturning circulation, the MOC, of the Atlantic Ocean will slow down and at the end of during the 21st century. Temperatures in the Atlantic region are projected to increase despite such changes to much larger warming associated with projected increases of greenhouse gases. Uh, and I'm going to take a small break here because I'm thirsty and maybe you would like to go to visit the toilet. Okay, yeah, I'm back for the last few sheets. Were there any questions that came bubbling up while I was gone? No? Guillermo, no questions? No? Okay. I'll continue for my rapt audience. Uh, yeah. So why should we worry about the climate anyway? Why should we worry? Uh, because obviously we want to have a good environment in which we live. That's one reason to worry. But yeah, you can see it as your responsibility, as your job, as Rania says. Um, but there's more to it than that also. Have you thought about the 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 impact of extreme weather, floods and tornadoes and other extreme weather? They have a very large effect on the economy. Yeah. So also, Danny, could you shut the door behind you? So they have calculated the annual losses in dollars in thousand million US dollars. So that's a billion in US English. The impact is for the next few years, 1970, 80, 90. That has been $50 billion in some years, and they expect this to increase even more. Extreme weathers. extreme weather. Yeah. Yeah, exactly. So there's damaged the crops that die, the tornadoes, not tornadoes, the hurricanes and monsoons getting wetter and or drier. So this is, and of course, then there's the water in places like Los Angeles and Cairo. It'll be more scarce and more difficult to come by. Yeah. So that's a very important reason. So if you can't convince people to save the planet for the planet's sake, uh, that's a link we can go to. Thank you, Anthony. Yeah, to me, I haven't seen this one, but it's like you just denying math. It's like denying 1 + 1 is 2. It's so to me it's so basic that global warming is an actual fact. It's climate change is a fact. But you can talk about the models and the scenarios, but it just is a fact. We've seen it in the last 50 years. It's nothing new. So the temperature increases again to 2080 are expected to be quite high. So beyond what we talked about before. And now we'll think about doom and gloom. So I've talked about the scenarios. If we don't take drastic situation, drastic drastic changes, we can bring them down, of course. Uh, but yet we take very drastic. Even if we stop totally, the levels will go down, not for another 100 years. So what some people are saying is that if we start now, we may be able to reverse the effects in the even longer term. So in the next 50, 60 years, there's no way we can stop it. But if we take a large mitigation, if we use energy, renewable energy, the levels will slowly break down. And why? Why does it take so long? Anybody? Why does it take so long for the CO2 and the methane to come out of the atmosphere? Any idea? Yeah. Well, we stop producing it. Right, well, yes. So exactly. It's funny. I'm getting two answers, and together they're the perfect answer. Yes. So Luke is correct. We had 100 years of production of CO2, and it's been pumping it into the air pretty quickly in the last few years. So I'm going to say slowly, but actually pretty quickly. And the only reason, really, way to get CO2 out, there are two ways. One is by plants. They convert CO2 to sugar, yeah, through photosynthesis. We all know that. I certainly hope. But the other way is, of course, through rain. Uh, that's why rainwater is slightly acidic. It has carbolic acid in it, which goes into the oceans, which are also a reservoir. So it just takes a very, very, very long time for the CO2 to either precipitate, I can't say that word today, precipitate out of the atmosphere for, by example, rainfall, or to be taken out of the atmosphere by trees, photosynthesis. Well, uh, it, a shortage of carbon dioxide. Well, we used to have no oxygen on our planet if we go back 6 billion years ago, but it's just for us. We like the planet the way it is. We like to breathe oxygen and have safe houses. It's also all relative. I guess plants love the increased level of CO2. Maybe not being chopped down as much, but well, different plants. Yeah. Yeah. Well, there's a reservoir. There's also it's a carbon reservoir. So yeah. So we think about the nutrient cycle. Maybe you've seen nutrient cycles. We've talked in this project. We're interested in nitrogen and phosphorus. Yeah. But the third most important is the carbon cycle. I really hope everybody in essence has studied that. Everybody else has studied that at least one time. The carbon cycle is CO2, CH4 in the air, um, carbon in trees, and in us, we are also a carbon reservoir of sorts. And the ground, there's a lot of carbon, but that's normally locked up in like oil reservoirs. And then, of course, the oceans. So those are the main reservoirs. And if it's in the atmosphere, it has to go to these other reservoirs, and that just takes a long time. Yeah. So in here we have the percentage reduction relative to baseline and the different scenarios. Yeah. So if we can get down to 450 parts per million or 550, so 450 that would be pre-industrial levels. Yeah. Of relative to baseline of CO2. And then also the precipitation would be less of an impact. Remember before we saw very large red. This is difficult to see. Large red bands and more orange. It's more stable in 2080. Hmm? Huh? So these now are based on regional changes uh, in the different scenarios. So here we have a small increase in rain, uh, inconsistent, so not so sure, but relatively stable. Uh, Again, this here's a picture of the Arctic summer, and right now, present day, we have Arctic ice. This is during the summertime. So in the summertime in the north, it's uh, in July and August, and here you see that the ice will disappear in the 2080s. Sea levels will rise. For who can name at least two reasons why the sea levels will rise? Anybody? Ice melting. Number one, yeah. And the second one, water expands. Yeah. No. Uh, water when it freezes, it expands. Yeah, but that's for certain levels. But it also expands as it's getting warmer at higher levels and on a very large scale. Long-term changes beyond. So now we're talking about in thousands of years. Huh? Well, mostly it's just from water entering in the system, but also expanding. And Danny is thinking about ice expands even more, um, but water itself also expands. Not as much as ice does. Total carbon reserves. Here we see converted resources, conventional resources. Yeah, coal. These are our carbon reserves. And orange is conventional reserves for the normal estimate, and this is the upper estimate. Uh, Oil, conservative and upper estimate. So there's a lot of debate about how much oil is left on our planet, how we get to it. This will include large pockets of reserves, but also in shale. So it's called fracking to get that out. Um, and it's true that a lot of it is predictions. We haven't found all of the oil, but we think it's out there. And there's a lot of debates about how much oil is left. Okay, so a few last bits and bobs, a summary before we close the lesson, and it's also the final lesson, so we're closing the course. Global average temperatures and sea levels are projected to rise under all IPC scenarios. Yeah, so that's the Intergovernmental Panel on Climate Change. I see that those links. I think in the first class talked about that. Temperature is expected to increase between 1.4 and 5.8, and these are the averages of the scenarios calculated by the models. And some of the models were higher, but this is the average of all the models. In general, there will be an increase in precipitation, of course, because water is evaporating at a higher amount, but this is variable. The weather patterns are expected to move towards the poles, creating, of course, more weather in the north, wet weather in the north and the south, and more droughts around the subtropical areas. Extreme events, so an increase in variability and of extreme events like hurricanes, monsoons. So here also. El Nino, they expect a little bit of a change, a small increase in amplitude, partly mitigated by the fact that there's just less rainfall, so the El Nino will have a smaller effect. The monsoons increase in Asian monsoon summer. A monsoon is the rainy season of Southeast Asia, and there's lots of rain. It rains for months. In Africa, they also have monsoons on the west coast of Africa. Huh? Yeah, it's warm because, of course, the temperature's warm. It's you know. The circulation of the wind, it will weaken, but not shut down completely. Snow and ice cover decreases, but Antarctica gains mass as Greenland loses ice. Sea level will raise between 9 to 88 centimeters. 9 to 88 centimeters, normally due to thermal expansion of water. And even if we stopped now, anthropogenic climate change will persist for many centuries. Even if we start now, because it just takes that much time for CO2 or carbon to get into plants and into the ground and into the waters. Anthropogenic means anthropos is Greek for human, and genic is generated, so it's generated by humans. Anthropogenic. I'm sure, yeah. Yes, they do. They do. That's it's very difficult. Yeah, it's the dual side of technology. Yeah, so technology causes problems like car exhausts, but technology also solves problems like renewable energy. Uh, they do take into consideration. I've even seen models where they take into consideration scientific errors. They're of their own models. They're like, we assume that our model, this assumption is be proven incorrect, but like 10% of all of our assumptions will be proven incorrect. And what's the variability of our model if they are quite advanced models. Okay. Uh, any more questions about the assignments too, or there are 4 assignments. It's on Blackboard and the syllabus. The question is, so when are the other ones due? On the top of my head, I don't know. I think the third one is the end of the month, and the last one is at the beginning of October. But for the exact dates, oh wait, I can check Blackboard for you. Yeah, you can do them now. There's no time like the present, but you do, of course. Now you have your plan of approach. Uh, some people have redos of, yeah, it's due tonight. Yeah. Let's hope. You might have a redo of the plan of approach if it's not accepted. Uh, it's prepare for the field week. You have a couple of you've really some busy weeks. The first 2 weeks are the busiest. Lots of classes, lots of assignments. But then you have the field week, which is also very busy. You have a little break, the Finland week, and then you're in the labs. You're in the Yeah, there's no classwork and weeks 3 to 10. Okay, so I'm seeing the third assignment is due on the 28th. Danny, your third assignment is due on the 28th, and the fourth assignment is due on the 2nd of October. There's no time like the present. Yes, and it's in the homework. It says that. It says complete sentences.